The section 2 of the chapter 5, heat transfer properties, is about lattice thermal conductivity. Let me first recall the Fourier's law, which is the heat flow Q is equal to minus the thermal conductivity times the temperature gradient dt over dx. So the heat flux Q is proportional to the temperature difference delta T and inversely proportional to the distance x. The reason for the proportionality of the heat flux to the temperature difference is easy to understand. However, the origin of the inverse proportionality of the distance is not obvious. The reason is clear by remembering the heat transfer in a space. We already discussed the heat transfer between surface A and surface B in space. The heat flux Q is equal to the Stefan-Boltzmann constant sigma times the temperature difference delta T times the average temperature cubed. So the heat flow Q is a function of the temperature difference delta T, but not a function of the distance x. Therefore, we cannot define the thermal conductivity of space. The inverse proportionality to the distance is the central issue of the lattice thermal conductivity. So the open question is why the heat flow is inversely proportional to the distance in metals. The answer is there is a function that prevents the heat flow in metals. This function preventing the heat flow is referred to as thermal resistance. The thermal resistance makes carrier particles turn around or annihilate and emits carrier particles. So this illustration shows the case of the radiative heat transfer in air, in space. So one side emit the photon, and it reaches the other side without any obstacles. But in this case, there is no thermal resistance. However, in the matter, the particles to carry heat is turn around in many points in the matter. Or sometimes it is absorbed and matter emits a new particle of heat. So in the standpoint of heat is transferred by phonons in quantum mechanics. Phonon is a quantum particle of the lattice vibration. This carrier particle is the phonon. Here, let us introduce the concept of the mean free path, which is the distance where a particle can run without colliding any obstacle. The heat flow Q is proportional to the mean free path SL. In the quantum mechanics, the lattice thermal conductivity is therefore given in the following formula. K is proportional to the product of N, C, V, L. N is the number of phonons per volumes, and C is the heat capacity per one phonon, and V is the average velocity of phonons, and which is equal to large C VL, and large C is the product of N and C, which is therefore the large C is the heat capacity per volume. Equation 5.2.2. Under these concepts, an open question is again, what works as the thermal resistance? If the atomic force is perfectly proportional to the displacement, the propagating lattice vibration goes straightly and is not attenuated because it is harmonic oscillation. And even if two waves intersect, two waves go straightly without interaction. Therefore, lattice vibration, propagation of the lattice vibration does not collide with anything within a crystal. So, in this case, there is no thermal resistance of the lattice thermal conductivity. Then, in what case the propagation of the lattice wave is prohibited or disturbed? There are two main causes for the thermal resistance of the lattice thermal conductivity. One is defects in the lattice, namely vacancy, impurity, dislocation, stacking fault, and so on. They are important at low temperatures. This means they are not important for geophysics because the Earth and the planetary interiors are at high temperatures. The other cause is the anharmonicity of the atomic potential. This figure shows the anharmonicity of atomic potential. The horizontal axis shows the atomic distance and vertical axis is atomic potential. At the bottom of the atomic potential, this curvature can be approximated by a parabola. This is regarded as harmonic potential. However, when energy is high and atoms vibrate at the high position of the atomic potential, the atomic potential cannot be regarded as harmonic but unsymmetric. Then this unsymmetricity or deviation from the harmonicity causes the thermal resistance of the lattice thermal conductivity. This effect is important or significant at high temperatures. Therefore, this is essential for geophysics. Here, let us argue how the anharmonic potential disturbs the propagation of lattice wave. The base of the argument is almost the same as the cause of the thermal expansion. So let us consider an atomic potential Ux which could be approximated by the second and third order polynomials. Equation 4.2.4. If the atomic potential were harmonic, the potential can be written Ux is equal to A1x squared. In this case, the equation of the motion for this atom is m times the second derivative of displacement x with respect to time is equal to the force, which is equal to minus the partial derivative of the atomic potential with respect to displacement from the equilibrium position, and which is equal to minus 2a1x. Then the solution of this equation is x equal a times cosine omega t. And omega is square root of 2a1 over m. M is the weight or mass of the atom. Then we come back to the anharmonic oscillation by taking into account of the a2x cubed term. So the potential is a1 times x squared plus a2 times x cubed. Then the equation of motion becomes m times the second derivative of the displacement x with respect to time is equal to minus 2a1x minus 3a sub 2x squared. Then we can simplify this equation as the second derivative of x with respect to time t is equal to minus omega squared x plus phi x squared. Here phi is minus 3a sub 2 over m. Here we assume a much smaller contribution of the higher order term, namely the magnitude, the absolute value of omega squared x is much larger than phi omega phi x squared. For the first approximation, the solution of the equation 5 to 9, the second derivative of the displacement x with respect to time t is equal to minus omega squared x plus phi x squared is assumed to have a formula with a slightly different angular frequency, omega prime. So x is equal to b, the constant b times cosine omega prime t. Here the omega prime is nearly equal to omega, or at least the difference between omega and omega squared is much smaller compared to omega squared. Then, however, this solution should be improved to increase the accuracy. Then, the equation 5 to 9 is modified by adding omega prime squared x term to the both sides. Then left side is the second derivative of x with respect to time plus omega prime squared x is equal to minus omega squared minus omega prime squared x minus phi times x squared. Then we substitute the approximate solution b cosine omega prime t into equation 5 to 12. Then we have the second derivative of the displacement x with respect to time plus omega prime squared x is equal to minus omega squared minus omega prime squared b times cosine omega prime t plus phi times b cosine omega prime t squared. Then this b cosine omega prime t squared is modified into cosine 2 omega prime t plus 1 over 2. Then we have equation 5 to 13. The equation 5 to 13, the second derivative of x with respect to time plus omega prime squared x is equal to minus omega squared minus omega prime squared b cosine omega prime t plus phi b squared omega 2 cosine 2 omega prime t plus 1 over 2. This equation, left side is x composed of x and its derivatives, and right side is composed of cosine omega prime t and cosine 2 omega prime t and constant term. We assume the solution of 5 to 13 have a form of C1 cosine omega prime t plus C2 cosine 2 omega prime t plus C0, equation 5 to 14. Then we substitute this assumed solution into 5 to 13. We have these equations, and we compare the factors of the cosine 2 omega prime t term. Then minus 3 omega prime squared c2 is equal to plus 5 b2 b squared omega over 2, and the omega prime t term, cosine omega prime t term is 0 equal minus omega squared minus omega prime squared times p. Because we assume approximate omega squared minus omega prime squared is nearly 0, we can consider b is non-zero, and the constant term is omega prime squared c0 plus phi b squared over t. From this argument, we can say that a particular solution for equation 5 to 9, the second derivative of x with respect to time t is equal to minus omega squared x plus phi x squared is c1 cosine omega prime t. The c1 was not determined in the previous argument, but the second term is the second harmonics term, cosine 2 pi omega prime t. Its factor is phi b squared over 6 omega prime squared, and we have a constant term phi b squared over 2 omega prime squared. We assumed the solution of the 5 to 9 is approximately b times cosine prime t. Therefore, by comparing this equation and this equation, we can conclude C1 is nearly equal to b. Therefore, the solution of equation 5 to 9 is approximately b times cosine omega prime t plus phi b squared over omega prime squared cosine 2 omega prime t plus phi b squared over 2 omega prime squared, equation 5 to 17. So, what does the equation 5 to 17 means? You can see the factor of the cosine omega prime t is b, but the factor of the cosine 2 omega prime t, the second harmonics term, is have a factor of b squared. The higher term of the potentials produce higher harmonic oscillation, this term, and the amplitude of the higher harmonic oscillation increases with the amplitude squared of the base wave b. So this means if two waves with the same amplitude intersect, the amplitude at the intersection becomes twice larger, because this b times twice larger. As a result, the amplitude of the higher harmonics become 4 times larger. Therefore, intersection of waves produces a larger magnitude of higher harmonics oscillation. In chapter 3, we learned that the wavelength of lattice vibration cannot be shorter than the twice of atomic distance, and the waves shorter than 2 times atomic distance are identical to long waves propagating opposite to the original wave. This animation shows such situations. These black dots are atoms, and this red wave propagates into left. However, this wave is very short, and this vibration, atomic vibration, is identical to the wave with the black curves. And you can recognize red wave and black wave propagates in the opposite directions. Let us argue the intersection of two lattice waves more accurately and precisely. The intersection of two lattice waves is expressed using the phonon scattering in quantum physics. This drawing shows the concept of the phonon scattering. This is in the reciprocal space, and this square indicates the first Brillouin zone. These green arrows indicate the wave vectors of two lattice waves, Q and Q prime. The intersection of these two lattice waves produces the another lattice wave, Q double prime, whose wave vector is sum of the wave vectors of Q and Q prime. In this case, the total momentum is held. Therefore, this lattice phonon scattering does not work as a thermal resistance of propagation of lattice wave. However, if the sum of Q and Q prime is large and resultant lattice wave is located out of the first Brillouin zones, situation is different. This broken arrow shows the sum of the original two lattice waves, Q and Q prime. As we learned in the chapter 3, when the wave vector is located out of the first Brillouin zone, such wave is identical to lattice wave whose wave vector is different by the lattice vector, reciprocal lattice vector G. So this broken arrows lattice wave phonon vector is identical to this red solid arrow Q double prime. As a result, the sum of the lattice wave Q and Q prime oriented in the different or opposite direction from the sum of original two lattice waves. This is referred to as Umklapp scattering, and as you can see, this process produces the momentum of a lattice wave in the opposite direction, and therefore it works as the thermal resistance of lattice wave propagation. Therefore, this is the origin of a thermal resistance of lattice thermal conductivity. Here, let us argue the temperature dependence of the Umklapp process leading to the temperature dependence of lattice thermal conductivity. Let us come back to this equation about the oscillation of the atom under anharmonic potential. You can see the amplitude of the harmonics is proportional to the amplitude of the original wave squared. This means the rate of the production of the harmonic waves increases is increase with the increasing amplitude, and the amplitude of the lattice wave is proportional to the temperature. As a result, if temperature is high, then the amplitude of the lattice wave becomes larger. Then the production rate of the harmonics become higher. Then Umklapp scattering become more intense. Then thermal resistance become larger, leading to the lower lattice thermal conductivity. Therefore, we can expect that the lattice thermal conductivity should decrease with increasing temperature. As we discussed, thermal resistance, or equivalently Umklapp scattering, and thermal expansion are both caused by the anharmonicity of lattice vibration. Therefore, the thermal conductivity and thermal expansion should have opposite dependence of pressure, temperature, and structure. If the atomic distance increase or decrease, anharmonicity increase and decrease. Then when temperature increase, the atomic distance increase. As a result, thermal conductivity decrease, but the thermal expansion increase. By compression, the atomic distance decrease, therefore thermal conductivity increase and thermal expansion decrease. Even when compressed, but the coordination number increase, then atomic distance increase even though volume decrease. As a result, thermal conductivity decrease and thermal expansion increases. So let us see the thermal conductivity of mantle minerals. This diagram shows the thermal conductivity of olivine, wazirite, ringodite as a function of temperature. You can see all thermal conductivity decreases with increasing temperature. The phonon mean free path decreases almost inversely from the to the temperature. As a result, thermal conductivity decreases nearly inversely to the temperature. By increasing pressure from, in this case olivine, from 0 to 4, 7, 10, 14 GPa, thermal conductivity increases. One reason is the phonon velocity increase, but a more essential reason is the phonon mean free path increase because the lattice spacing decrease and the harmonicity of the lattice vibration decreases. This slide shows the change of thermal conductivity with phase transition in coordination number change. The working sample is potassium chloride. Potassium chloride shows the B1, B2 transition with increasing pressure around 2 GPa. B1 structure coordination number is 6 and B2 structure coordination number is 8. So in the stability field of B1 phase, the thermal conductivity increases with increasing pressure, certainly due to the atomic distance decrease by compression and the anharmonicity of the lattice vibration decrease. With the phase transition, the thermal conductivity decreases. This is because of the bonding length increase with the B1, B2 transition. This diagram shows the potassium chlorine bonding length. In the this is a stability with pressure. This is a stability field B1 phase, and this is a stability field B2 phase. Please note that this pressure is in kilobar, and this is a pressure in GPa. Here B1 to B2 transition occurs. And in the stability field of B1 phase, the bonding length continuously decrease, but with the transition to B2 phase, bonding length increase and then decrease. The decrease of the thermal conductivity at 2 GPa should correspond to the this bonding length increase by the B1 to B2 phase transition. So this is the end of the section 2, that is thermal conductivity.